Imagine being able to analyze and understand the vast amounts of text data that surrounds us. From social media posts to news articles and even conversation with chatbots, natural language processing is the key to unlocking this power, and it's a fascinating field that combines computer science, linguistics, and artificial intelligence. In this video, we will take you on a journey through the basics of text processing, including tokenization, morphology, and stemming, as well as more advanced topics like language modeling, pause tagging, parsing, and text classification. We'll explore popular libraries like NLTK and spaCy and delve into the world of word embeddings, TF-IDF, and other lexical similarity measures. So whether you are a beginner or an experienced developer, this video will give you a comprehensive introduction to the world of NLP, covering topics like n-gram modeling, smoothing techniques, Perplexity, and Viterbi algorithm. So join us on this exciting journey and discover how NLP can help you extract insight, sentiment, and meaning from text data and unlock new possibilities for your projects and applications. So let's get started with understanding text processing. Basically, text processing is a crucial step in natural language processing that involves cleaning, tokenizing, and normalizing text data. So here we will cover the basics of text processing using NLTK, spaCy, morphology, stemming, and edit distance. So first comes the NLTK, which is a popular Python library used for NLP tasks. It provides tools for tasks such as tokenization, means breaking down text into individual words or tokens. Stop word removal means removing common words like the, and, etc. that don't add much value to the text. Stemming means reducing words to their base form. Lemmatization means reducing words to their base or root form. Next comes spaCy, which is another popular Python library for NLP that focuses on performance and ease of use. It provides features like tokenization, where we break down text into individual words or tokens, part of speech tagging, where we identify the grammatical category of each word. Named entity recognition means identifying named entities like people, places, and organizations. Dependency parsing means analyzing the grammatical structure of the sentence. Next comes morphology, which is the study of internal structure of words and how they are formed from smaller units called morphemes. So morphemes are the smallest unit of language that carry meaning. For example, the word unhappiness can be broken down into its morphemes. Un, that is prefix, happy is the root word, ness is the suffix here. Next comes the stemming, which is the process of reducing words to their base form by removing suffix. And there are various stemming algorithms like Porter stemmer, which is a simple and widely used stemming algorithm. Next comes snowball stemmer, which is more advanced stemming algorithm that handles irregular words. For example, the word running can be stemmed to its base form run using a stemming algorithm. Next comes edit distance, which is the measure of number of operations required to transform one string to another. Here the operations can be insertion, that is adding a character to the string, deletion, that means removing a character from the string, substitution means replacing a character with another. For example, the edit distance between the strings kitten and sitting is 3 because we need to perform the 3 operations here. First, substitute S for K, then substitute I for E and append G to the end of the string. Next comes its example use case. So suppose we want to build a chatbot that can respond to user queries. So here we can use text processing techniques like tokenization, stop word removal, and stemming to pre-process the user's input and then use a machine learning model to generate a response. For example, if the user asks, "What is the weather like today?" we can tokenize the input into individual words like "What is the weather like today?" Here we can then remove stop words like is and the and stem the remaining words to their base forms. So what will remain what? Weather will stem into with and rest all will remain same. So here we can use machine learning model to generate a response based on this pre-processed input. Next comes the language modeling, which is a crucial task in natural language processing that involves predicting the next word in a sequence of words. So in this explanation, we'll cover the basics of language modeling using n-gram modeling, smoothing techniques, and Perplexity. First comes n-gram modeling, which is a simple and widely used language modeling technique because it involves predicting the next word in a sequence based on the context of previous n words. For example, if we want to predict the next word in the sentence, "I love to eat," we can use 2-gram model, also called bigram model. that looks at previous two words, love to predict the next word. Here, the probability of the word sequence can be calculated using this formula, where this PWI by Wi minus 1 and all is the conditional probability of the word Wi given the context of previous words. Next comes the types of n-gram models, where first is unigram model, which looks at the previous word to predict the next word. Bigram model, which looks at the previous two words to predict the next word. Trigram model looks at previous three words to predict the next word. And finally, n-gram model looks at previous n words to predict the next word. Next comes smoothing techniques, which are used to handle the problem of zero probability in n-gram models. So when a word sequence is not seen in the training data, the model assigns a zero probability to that sequence. And there are various smoothing techniques like Laplace smoothing, which adds a small value to the numerator and denominator of the probability formula to avoid zero probability. Good Turing smoothing uses a more sophisticated approach to estimate the probability of unseen word sequences. And finally, this Nizar-Ney smoothing uses a combination of Laplace and Good Turing smoothing to estimate the probability of unseen word sequences. Next comes the perplexity, which is the measure of how well a language model predicts the next word in a sequence. It is calculated using this formula, where this n, caps of n, is the number of words in the test data, and this PWI by all is the conditional probability of the word WI given the context of previous words. Here, the lower probability score indicates a better language model. So for example, we take a use case. Suppose you want to build a language model for the chatbot that can respond to user queries. So here we can use n-gram model to predict the next word in the user's input and then use a machine learning to generate a response. So for example, if the user asks, what is the weather like today? Here we can use a 2-gram model to predict the next word in the sequence. Like here, what is that's probability is 0.8, then is here the probability is 0.7 and so on. So we can use a machine learning model to generate a response based on the predicted word sequence. Next comes the pause tagging. Basically, parts of speech tagging is a fundamental task in natural language processing that involves identifying the grammatical category of each word in a sentence. So in this explanation, we'll cover basics of pause tagging using sequential learning, hidden Markov models, and Viterbi algorithm. So first comes the sequential learning, which is a type of machine learning that involves predicting a sequence of labels or tags based on the context of previous labels or tags. So here in pause tagging, sequential learning involves predicting the pause tag of each word in a sentence based on the context of previous words. For example, if we want to predict the pause tag of the word running in the sentence I am running, we can use sequential learning to predict the tag based on the context of previous words I and am. Next comes hidden Markov models, which is a statistical model that can be used for sequential learning tasks like pause tagging. Here, hidden Markov models consist of three components. First is the state, that is the possible pause tags, for example, noun, verb, adjective, etc. Observations, these are the words in the sentence, and transitions are the probabilities of moving from one state to another. So hidden Markov models can be represented as a graph where each state is a node and the transitions are the edges between the nodes. Next comes Viterbi algorithm, which is a dynamic programming algorithm used to find the most likely sequence of states or the pause tags that generated a given sequence of observations. And this algorithm works by initializing a trellis, that is a two-dimensional array with the probability of each state at each time step, then filling in the trellis using the transitional probabilities and the observation probabilities, then back tracing through the trellis to find the most likely sequence of states. Basically, this Viterbi algorithm is used to find the most likely pause tag sequence for the given sentence. Next comes its use case. Suppose we want to build a pause tagger for a chatbot that can respond to user queries. Here we can use this hidden Markov model and the Viterbi algorithm to predict the pause tags of each word in the user's input. For example, if the user asks, what is the weather like today? We can use hidden Markov model and Viterbi algorithm to predict the pause tags of each word like this given below. So here we can use the predicted pause tags to generate a response based on the user inputs. Now the key concepts which we have discussed till now is tokenization, which means breaking down text into individual words or tokens. Tagging means assigning a label or tag to each token. Sequential learning means predicting a sequence of labels or tags based on the context of previous labels or tags. Hidden Markov model is a statistical model that can be used for sequential learning tasks. And finally, this Viterbi algorithm is a dynamic programming algorithm used to find the most likely sequence of states, that is pause tags that generated a given sequence of observations, that is words. Next comes the common pause tags, which is noun, that is a word that refers to the person, place, thing or idea. Verb, which is a word that expresses action or state of being. Adjective is a word that modifies or describes a noun or pronoun. Adverb is a word that modifies or describes a verb, adjective or other adverb. Pronoun is a word that takes the place of noun in a sentence. Next comes the parsing, which is a fundamental task in natural language processing that involves analyzing the grammatical structure of the sentence. So in this explanation, we'll cover the basics of parsing using constituency and dependency parsing, CKY algorithm, context-free grammar, and probabilistic context-free grammars. So first comes the constituency parsing, which is a type of parsing that involves breaking down a sentence into its constituent parts such as phrases and clauses. For example, the sentence, "The dog chased the cat," can be broken down into the constituents like they're shown below. So next comes the dependency parsing, which is a type of parsing that involves analyzing the grammatical dependencies between the words in a sentence. For example, the sentence, "The dog chased the cat," can be analyzed like this. The, that is a determiner, depends on the dog, which is noun. Here dog depends on the verb chased. So like this. Next comes a CKY algorithm, which is a parsing algorithm that can be used for constituency parsing. Basically, it's a dynamic programming algorithm that works by breaking down the sentence into its constituent parts, building a parse tree from the bottom up, and using a table to store the parse trees for each sub-sentence. So this CKY algorithm is efficient and can be used for parsing sentences with complex grammatical structures. Next comes context-free grammars, which is a set of production rules that can be used to generate a language. It consists of terminals or the basic symbols of the language, say words. Non-terminals means the symbols that can be replaced by other symbols, say phrases. Production rules are the rules that govern how the symbols can be combined. For example, context-free grammar for a simple language might include these production rules, where S, that is a sentence, consists of the noun phrase and the verb phrase, then NP to det n, that is a noun phrase, consists of determiner and a noun, and so on. Next comes probabilistic context-free grammars, which is a context-free grammar that assigns probabilities to each production rule. It's a way of modeling the probability of a sentence being grammatically correct. For example, probabilistic context-free grammar for a simple language might include the production rules with the probabilities as shown here. Here the probabilities are learned from the training corpus and can be used to predict the probability of a sentence being grammatically correct. Next comes its example use case. So suppose you want to build a parser for a chatbot that can respond to user queries. Here we can use both context-free grammars or probability-based context-free grammars to define the grammar of the language, and then using the context-free grammar or the CKY algorithm to parse the user's input. For example, if the user asks, "What is the weather like today?" we can use this context-free grammar or the probability context-free grammar to parse the sentence and identify the constituent parts. So like, what is the interrogative pronoun? Is this the verb? So then we can use the parse sentences to generate a response based on the user queries. Next comes the key concepts which are discussed till date. So that is a tokenization, means breaking down text into individual words or tokens. Parsing means analyzing the grammatical structure of the sentence. Constituency parsing means breaking down the sentence into its constituent parts. Dependency parsing means analyzing the grammatical dependencies between the words. CKY algorithm is a parsing algorithm for constituency parsing. CFG is a set of production rules for generating a language, and this probabilistic context-free grammar is a context-free grammar that assigns probabilities to each production rules. Next comes the common parsing term. Parse tree means a tree-like representation of grammatical structure of sentence. Non-terminal is a symbol that can be replaced by other symbols. Terminal is the basic symbol of the language. Production rule is a rule that governs how symbols can be combined. And probability is a measure of the likelihood of sentence being grammatically correct. Next comes the parsing algorithm. So CKY algorithm is a parsing algorithm for constituency parsing. Arley algorithm is the parsing algorithm for constituency parsing. And this top-down parsing is a parsing algorithm that starts with the overall structure of the sentence and works down to the individual words. Bottom-up parsing is a parsing algorithm that starts with individual words and works up to the overall structure of the sentence. Next comes the applications of the parsing. So first, the language translation. Here parsing is used to analyze the grammatical structure of sentence in one language and generate equivalent sentence in another language. Text summarization. Here parsing is used to identify the main ideas and concepts in a text and generate the summary. Also parsing is used to analyze the sentiment of text and determine whether it is positive, negative or neutral. Finally, parsing is used to analyze the grammatical structure of questions and generate answers. Next comes the challenges in parsing. So this parsing can be challenging when there are multiple possible interpretations of sentence. Also, parsing requires a deep understanding of the context in which a sentence is being used. Parsing can be challenging when dealing with the languages that have complex grammatical structures or variable word order. Also, parsing can be challenging when dealing with large volumes of text data. Next comes the future of parsing. Well, deep learning techniques are being used to improve the accuracy and efficiency of parsing algorithms. Also, parsing algorithms are being developed to handle multiple languages and dialects. Parsing algorithms are being developed to analyze text in real time and generate responses. And finally, parsing algorithms are being developed to provide explanation for their outputs and improve transparency. Next comes the text classification, which is a fundamental task in natural language processing that involves assigning a label or category to the piece of text. So in this, we will cover the basics of text classification using Naive Bayes algorithm and lexical similarity measures like word embeddings, TF-IDF, word-to-vec and glow. So first of all, we will cover the Naive Bayes algorithm, which is simple and widely used algorithm for text classification. It is based on Bayes theorem and works by calculating the probability of each word in the text given the label. Also calculating the probability of label given the text. Finally, multiplying the probabilities together to get the final probability of label. So this Naive Bayes algorithm is simple to implement and works well for many text classification tasks. However, it assumes that the words in a text are independent, which is not always the case. Next comes the lexical similarity measures, which are used to compare the meaning of words in a text. And there are different types of lexical similarity measures like word embeddings. So word embeddings are a way to represent words as a vectors in high dimensional space. They are trained on large amount of text data and can capture subtle differences in word meaning. TF-IDF means term frequency inverse document frequency is a measure of importance of word in a document. It is calculated by multiplying the frequency of word in a document by the inverse frequency of word in the entire corpus. Next comes word-to-vec, which is a type of word embedding that is trained using a neural network. It is designed to capture the semantic meaning of words and can be used for tasks like text classification and language modeling. Next comes GLOBE, that is global vectors for word representation, which is another type of word embedding that is trained using a matrix factorization technique. It is designed to capture the semantic meaning of words and can be used for tasks like text classification and language modeling. Next comes word embeddings, which are a powerful tool for text classification. They can capture subtle differences in word meanings and can be used to improve the accuracy of text classification models. And there are several types of word embeddings, including word-to-vec, which is a type of word embedding that is trained using a neural network. It is designed to capture the semantic meaning of words and can be used for tasks like text classification and language modeling. Next comes GLOBE, that is global vectors for word representation, which is a type of word embedding that is trained using matrix factorization technique. It is designed to capture the semantic meaning of words and can be used for tasks like text classification and language modeling. Fast text is a type of word embedding that is trained using a neural network. It is designed to capture the semantic meaning of words and can be used for tasks like text classification and language modeling. Next comes TF-IDF, means term frequency in words document frequency, which is a measure of the importance of word in a document. It is calculated by multiplying the frequency of words in a document by the inverse frequency of word in the entire corpus. Basically, TF-IDF is simple and effective way to weight the importance of words in a document. It is widely used in text classification and information retrieval tasks. For example, we want to build a text classification model that can classify text as either positive or negative. So here we can use the combination of naive-Bayes algorithm and word embeddings to build a model that is accurate and effective. And here is an example of how we might use word embeddings to build a text classification model. So first of all, pre-process the text data by tokenizing the text and removing stop words. Then train the word embedding model on the pre-processed text data. Then use the trained word embedding model to represent each text sample as a vector. Then train a naive-Bayes classifier on the vectorized text data, and finally evaluate the performance of classifier using the test set. And that's the wrap. A journey through the world of natural language processing has taken us from the basics of text processing to the cutting-edge techniques of language modeling, pause tagging, parsing, and text classification. Here we have explored the power of popular libraries like NLTK and spaCy and delved into the fascinating world of word embeddings, TF-IDF, and other lexical similarity measures. As we have seen, NLP has the potential to revolutionize the way we interact with text data, from chatbots and virtual assistant to sentiment analysis and language translation. With the continued advancement in text and the deep learning and machine learning, the future of NLP is brighter than ever, and we can expect to see even more innovative applications and breakthroughs in the years to come. So whether you are a developer, researcher, or simply a curious learner, we hope that this video has inspired you to explore the exciting world of NLP and unlock its full potential to transform the way we live, work, and communicate. Thank you.